All around your house, there's this hidden engine that's pretty much powering your entire life. It's called the single-phase induction motor. And while you've probably never actually laid eyes on one, you use dozens of them every single day. So today, we're going to pull back the curtain on this unsung hero of the modern world.
So let me ask you something. Think about the fan that cools you down, the blender that makes your smoothie, and the refrigerator that keeps your food from spoiling. What's the one thing that connects all of them? They seem totally different, but they all share the exact same heart.
You guessed it. The answer is that single-phase induction motor. It's in your washing machine, your vacuum, your power drill, your AC unit. I mean, the list just keeps going. And here's a crazy fact for you. The total number of these little motors completely dwarfs all the giant industrial motors in the world combined. They are, quite literally, everywhere.
And here's a peek inside. It's a really beautiful, simple, and tough design. It's got just two main parts, the outside part that stays still, called the stator, and the inside part that spins, the rotor. This elegant simplicity, that's exactly why it's so popular. It's cheap to make, super reliable, and it's perfectly built for the kind of power we have in our homes.
Okay, and this is the crazy part, this motor, the most successful and widespread motor in all of history, has a fundamental, almost unbelievable flaw. A paradox that should make it completely useless. Our source material really nails the problem with this one sentence. These motors have no inherent starting torque. So what does that mean in plain English? It means, by itself, it can't start. If you plug it in, it'll just sit there and hum at you, not moving an inch. Which leads us right to the central mystery we're going to solve. How on earth did a motor with what seems like a fatal flaw, the fact that it can't even get itself going, become the engine behind our entire modern lives? Let's dive in. To crack this puzzle, first we have to understand why it can't start. And the answer is pretty cool, actually. It's basically a war between two perfectly balanced, opposing forces. It all boils down to this idea called the double revolving field theory. Basically, you can think of the single pulsing magnetic field coming from your wall outlet as two separate fields. They're each half as strong, and they're spinning in opposite directions at the exact same speed.
This is the perfect way to picture it. Imagine a merry-go-round. You've got one person pushing it clockwise and another person pushing it counterclockwise with the exact same amount of force. What happens? Nothing, right? It's a perfect stalemate. The merry-go-round doesn't budge.
And this graph right here, it shows you that stalemate in black and white. It plots torque against speed. TF is the forward push and TB is the backward push. Now, look right there in the middle at zero speed. The two forces are perfectly equal and opposite. They completely cancel each other out. Net result? Zero torque. The motor is stuck. So, if the motor is naturally stuck in this perfect stalemate, how in the world do we get it moving? Well, this is where some seriously brilliant engineering comes into play. Engineers found a super clever way to give the motor a kick in just one direction, just for a second, to break that tie. The solution is something called split-phase starting. And here's the game plan. First, you add a second temporary starting winding. Then, and this is the key, you design this new winding to be electrically different from the main one. This difference basically tricks the motor into creating an unbalanced rotating magnetic field for just a moment. That imbalance is the push it needs to start spinning. And finally, once it's up and running, a switch just cuts that starting winding off. Simple as that. So here's the most basic version, the resistor split-phase motor. You can see the main winding, and right next to it, in parallel, is the starting winding, hooked up through a little centrifugal switch. When you power it on, both windings get juice. But as the rotor spins up to about 75% of its top speed, that switch gets flung open by the motion, and poof, the starting circuit is disconnected. The real secret sauce is making those two windings different. The main winding is built for efficiency, right? Low resistance, high reactance. Think of that as electrical inertia. But the starting winding? It's intentionally made the opposite way. High resistance. This difference is what causes the current in the two windings to get out of sync or out of phase, which is exactly what you need to create that initial rotating field.
And here is the result of that clever trick. Remember that first torque curve we saw where everything was stuck at zero? Well, look at this one. Right at the beginning, at zero speed, there is now a clear, positive starting torque, labeled TST. That's the push. That's the kick that breaks the stalemate and gets the whole thing spinning.
Now, this basic method works great for things that are easy to get going, like a fan. But what about appliances that need a much bigger shove to get started, like the compressor in your refrigerator? For that, engineers needed an even more powerful kickstart. Check this out. On the left, you've got the resistor start circuit we just talked about. On the right is the upgrade. The only big change is the addition of one little component, a capacitor, dropped in line with the starting winding. This one tiny change makes a massive, massive difference.
This bar chart shows you exactly why that little capacitor is such a game changer. It's way better at shifting the current's phase. The resistor method only gets you about a 25-degree difference, but adding the capacitor bumps that all the way up to around 80 degrees, which is so much closer to the perfect, ideal 90-degree split. And a bigger phase angle means a stronger, more efficient push at startup.
And a stronger field means, well, just look at this curve. The starting torque for a capacitor start motor can be over 300% of its normal running torque. That is the kind of brute force you need to kickstart a heavy-duty compressor in a fridge or an AC unit when it's under high pressure.
So what this all means is that engineers pick the right starting method for the right job. Simple resistor starts for things like fans. High-torque capacitor starts for heavy lifters, like refrigerators. And there are even other types, like the super quiet permanent capacitor motors you'll find in ceiling fans, or the incredibly simple shaded pole motors in small toys and hairdryers. Each one is just a slightly different solution to that same fundamental problem.
So in the end, it's really a beautiful story of ingenuity, isn't it? A fundamental stalemate baked into the laws of physics, a motor that couldn't start, was totally solved by a simple, clever trick, just temporarily shifting the phase of the current to give it a little nudge in the right direction. And it really makes you wonder. Every time you flip on a fan or open your fridge, you're watching the solution to this elegant paradox in action. So, what other invisible engineering marvels are hiding in plain sight, quietly making your world work every single day?